Hello everyone. In this video we're going to take a look at a couple of examples involving the Markov and the Chebyshev inequalities. So the quick overview is in the first example we'll see a couple of questions involving the Markov and the Chebyshev inequalities, and another in example 2, this one being slightly more complicated. All right, in example 1, let's consider Vincenzo Montella, a talented soccer player who is expected to score 21 goals in a given soccer season. So here you can see Vincenzo Montella. He was a member of the Italian Olympic soccer team. In part A, we want to find an upper bound on the probability that he scores 30 goals or more during the season. And in B, if he has a standard deviation of 6.5 goals during the season, give a bound on the probability that he scores between 8 and 34 goals during the season. So for part A, we need to use the Mark of Inequality, denoted in the book also as version 2, which tells us that for a given constant A that's positive, the probability x greater than or equal to A, this probability is less than or equal to the expectation of x over A. So in the example, we know that the average number of goals scored is 21. That gives us E of x. A is 30, so the probability x greater than or equal to 30 is equal to 21 over 30, or 0.70. For part B, we need to use the Chebyshev inequality, labeled as version 2 in the textbook, which tells us that for a constant k greater than 0, the probability that x minus e of x in absolute value is greater than k times the standard deviation, right? The probability of this happening is less than or equal to 1 over k squared. Or by flipping signs, which, formerly we're using the complement, we get that the probability x minus e of x is less than k sigma. Right here we change this sign, and then we flip this one, is greater than 1 minus 1 over k squared. So in the example, we know that e of x is 21. So the probability that x is greater than or equal to 8 and less than or equal to 34 is equal to the probability that the absolute value of x minus 21 is less than or equal to 13. Okay, so these two probabilities are equivalent, right? You just take this out and expand it. You'll see we get that x is between 8 and 34. And now if we break down the 13 into some multiple of the standard deviation, you see we get 2 times 6.5. So our value of k is 2. Right, looking right here, sigma is 6.5. So k must be 2. That's how we get to 13. So we know that the probability x is between 8 and 34 is greater than or equal to 1 minus 1 over 2 squared, and that's equal to 0.75. Again, we're getting k equals 2 from this sort of upper bound here by breaking down to 13. 2 times 6.5, that's how we get k is equal to 2. So that completes the solution to example 1. In example 2, okay, the logic of the solution is going to be somewhat similar. Well, let's say the average temperature in December is a nice, bitter cold 27 degrees. So we can imagine all sorts of snow outside, maybe even a snowman. In part A, we want to find a bound on the probability of the temperature falling outside the range of minus 50 to 50. So either below minus 50 or above 50. And in part B, if the standard deviation of the temperature is 7 degrees, then what's the probability that the temperature falls outside the range of 14 to 40 degrees? You can see in A, we do not need any sort of standard deviation, but in B, we will take advantage of a standard deviation. So for A, we'll use the Mark of Inequality, labeled version 1 in the textbook, which tells us that for an A greater than 0, the probability, the absolute value of A is greater than or equal to, take that back, the probability of the absolute value of X greater than or equal to A is less than or equal to E of X over A. So in the example, we were given that the average temperature is 27, that's our E of X, and A is 50. So we get that the probability X is outside this interval, which is equivalent to saying the probability the absolute value of X is greater than or equal to 50 is equal to 27, that's our E of X, over 50, that is our A. So you could see that this fraction simplifies to 0.54. For part B, okay, again, we use the Chebyshev inequality that tells us the probability absolute X minus E of X greater than K sigma is less than or equal to 1 over K squared. So notice that we're interested in the probability that X is between 14 and 40. We could express this in terms of absolute value. And you'll see that the actual midpoint of the interval from 14 to 40 is 27, which works out nicely because our E of X is 27. So the probability that the absolute X minus 27 less than or equal to 13, okay, it's equivalent to the probability we want. Now what we have to do to use Chebyshev's theorem is break this 13 down into some multiple times the standard deviation. We know the standard deviation is 7. So if we try to take K sigma, replace sigma with 7, so K times 7 equals 13, we could solve that. We get K is 13 over 7. Okay, so not quite equal to 2. K is 13 over 7. Now when we apply the Chebyshev inequality, okay, so I have the Chebyshev inequality with less than or equal to here. We know that'll be less than or equal to 1 over K squared. So we're looking at 1 over this fraction, 13 over 7 squared. So again, we sort of flip the fraction in the denominator, and we get 7 squared over 13 squared equals 0.2899. Any questions? Excellent. I hope you learned something from this video.